As you learned from the previous video, an overload relay is a sensory safety instrument that protects an electrical motor from a continual high current draw, preventing it from overheating. When the overload relay senses an overload condition that has persisted for a while, it will trip and notify a contactor of the problem, so the contactor interrupts the current flow and shuts off the motor. Please make sure to watch our previous video to make it easier for you to understand this tutorial. The link is provided in the description. One question that may concern your mind is, how does an overload relay trip? To answer this question, you need to get familiar with the mechanisms of overload relay types. There are two different kinds of overload relays, thermal overload relays and magnetic overload relays. Two types of thermal overload relays exist, bimetallic and melting alloy, and the two main types of magnetic overload relays are Dashpot and electronic. Let us review the first type of thermal overload relay, the bimetallic, which includes the following components: insulated rod, lever, a spring, normally closed contact number 95 to 96, normally open contact number 97 to 98, reset button, current adjustment screw, and the heating element, which is usually wrapped around the bimetallic strip separated by an insulator. The bimetallic strip is made up of two dissimilar metals stuck together that have a difference in coefficient of thermal expansion. It means when the strip is heated to a set temperature, the metal with a higher coefficient of thermal expansion grows faster than the other metal, and as a result, the bimetallic strip will bend. During normal working conditions, the bimetallic strip remains almost straight and holds the overload relay auxiliary contacts as it is. When an abnormally high current flows through the heating element, the bimetallic strip receives the heat produced by the heating element. And as a result, the strip bends and causes the insulated rod and lever to be pushed to activate the tripping mechanisms, which opens the normally closed contact, interrupts the electricity to contactor coil, and opens the power contact to stop the motor. After the overload condition is resolved, pressing the reset button will reset the auxiliary contacts, lever, and insulated rod to their original positions and resume normal functioning. The force needed to bend the bimetallic strip is regulated using the current adjustment screw. Once you set this screw to the higher FLA, it increases the tension in the tripping mechanisms, requiring the slide to exert more force to reach the trip threshold. After reviewing the bimetallic type, let's consider the melting alloy overload relay, which uses a melting eutectic alloy. It is a particular kind of metal that, at a set temperature, transforms from a solid to a liquid. The eutectic alloy is contained in a tube with a fixed inner shaft. This tube is attached to a ratchet wheel, and a pole is engaged in one of the ratchet wheel cogs. This pole is linked to the spring-loaded contact, which is held close and includes the reset button. A heater coil wraps around the exterior of the tube and is directly linked to the motor circuits. When an overload condition happens, excessive current flows through, causing the heater coil to heat up sufficiently to melt the inner eutectic alloy. So it enables the inner ratchet shaft to spin and releases the pole, causing the spring-loaded contact to open, first energizing the contactor coil and opening the power contact to stop the motor. When the eutectic alloy cools and solidifies and anchors the ratchet in position, the reset button can be pressed to reposition the pole in the cog and compress the spring, thus closing the contact. After exploring the thermal overload relay types, let us go over the magnetic types and start by understanding the dashpot. The dashpot overload relay consists of a plunger attached to a piston with a bypass hole called an orifice contained within an oil-filled cylinder assembly. It also has current coils linked to the motor power circuit in series and a normally open contact placed in the trip circuit of the motor. Under normal conditions, the magnetic flux created by the current coils is insufficient to cause significant movement of the plunger. Once the tripping current passes through the coils in the event of overloading, the magnetic field becomes more powerful, causing the plunger and piston to start moving upward against the displacement of viscous oil through the orifice. Due to the completion of upward movement of the plunger and piston, the normally open contact closes in the trip circuit and energizes the contactor coil, thus opening the power contact to turn off the motor. After understanding the dashpot overload relay, let us now look at the solid-state or electronic type that uses a CT mounted on each phase and circuit board for constantly monitoring the load current. A CT or current transformer is basically a wire wrapped around a piece of donut-shaped metal. The motor current passes through the metal, creating magnetic field that causes a smaller current to flow through the CT wire, which is then linked to the electronic board where the signal is analyzed. When continual overloading occurs, the created current flowing through the CT wire increases, which is then processed by the circuit board. After the internal circuitry finds out that the motor is pulling a high current, it will send a command to open the auxiliary normally closed contact, thus interrupting the power to the contactor coil and deactivate the power contacts to stop the motor. After reviewing different types of overload relays, it's time to answer this question. How long would it take for an overload relay to trip under an overload condition? Well, two different factors need to be considered: the amount of current flowing through and the trip class setting. Each manufacturer should provide a graph displaying tripping time as a function of current. On a logarithmic scale, this graph shows tripping time on the y-axis and illustrates current as a multiple of the overload current on the x-axis. Imagine the overload relay set to 9 amps and the motor drawing 27 amps consistently, so it is pulling 300% of what it should be or 3 times as much. Then you can go through the graph to see when the overload relay carries 3 times the 9 amps, it will trip after around 15 seconds. What about the role of the trip class? This factor does not appear as a variable in the overload relay graph since each curve is specified by a trip class. For example, this graph belongs to an overload relay with a trip class of 10. The trip class describes how long it takes for an overload relay to trip while carrying a current equivalent to 6 times its existing setting. For instance, for an overload relay with a trip class of 10, while carrying a current equal to 6 times its FLA rating, the overload relay will take 10 seconds or less to get tripped. Here is an illustration that shows 3 trip classes plotted on the same graph for comparison. We will compare them while they carry a current equal to 6 times their current setting. You find the curve of the trip class of 10 at the bottom since it causes the overload relay to trip quickly, in this case around 5 seconds. The next in the middle belongs to trip class of 20, tripping the overload relay around 18-ish seconds for this example. And finally, the top curve is dedicated to the trip class of 30, as it will take the overload relay to trip in the lengthier period, around 27 seconds in this example. Don't forget to share your opinion about this video in the comment section. Also, please encourage us by liking the video, subscribing to our channel, and pressing the bell icon to keep motivating us to produce more informative videos.